Hey everybody, how's it going? So in this video, I'm going to go over quadratic points, which is the newly retired crypto challenge from HackTheBox that's rated medium. Now I know I'm always going on about how meaningless ratings are and how you shouldn't pay attention to them, and that's all true. But I really wish they would have rated this challenge easy instead of medium, because from a crypto standpoint, there isn't really anything kind of complex going on. You just basically just need to be aware of kind of one concept. But I think it's an excellent challenge in terms of like the opportunity to like practice some skills or like be introduced to some tools that someone who hasn't done much crypto or CTF like might not be familiar with. And if it'd been rated easy, I think it's more likely they would have given it a go. I also think maybe that's why it doesn't have as high a rating as other challenges, because it's, I don't know, like I said, the crypto part is not very complex. But then I don't know. Mostly everyone rated it pretty squarely a medium. So what do I know? But anyway, like I said, in my opinion, I think this is a great challenge, especially to give a go if you maybe don't have lots of programming experience, with like algorithms, and or you've never used Pwn tools or Sage Math, or don't know anything about elliptic curves, because that's really mostly what this challenge is. But it's not too deep into any of those, so it's sort of like the perfect difficulty if you're like unfamiliar with any of those things. So anyway, let's just go ahead and jump into the code. So this is the code. I've already downloaded it, and this is what is running on the remote instance that we connect to, which is how we're going to end up getting the flag. If we look at this code, it just imports these are PyCryptodome functions. Then we have these two modules here, which we don't have access to. Obviously, right, if we did, we know the flag. And the other one is this utils. It's running on the server, but we don't know what the code is behind that. But essentially, it's their elliptic curve function and this find valid quadratic coefficient. And then we see there's this function here, which you don't need to worry about it. It's really well named because it does exactly what it says it does, gets an input, and there's a timeout. And when we connect to service, is kind of where the code starts here. So this is basically this for loop. Let me actually go ahead and it's going to connect just so you can see what it does. So we connect, says, hello, cryptographer, please enter the coefficients of the quadratic equation to proceed. And then it gives us this equation and gives us an x value, and then we need to solve it. I'm sure you've heard of like the quadratic formula. Basically, a quadratic is just a polynomial with degree 2. So like the simplest case is just ax squared plus bx plus c. And it's giving us the x, and so we need to solve, it's giving us an x, and we need to solve what do we make a, b, and c in order to equal 0, which is what we see is happening right here. So it gives us two of these, if you're wondering why it gives us two, but it only ever uses this one. So there's the fundamental theorem of algebra, basically says there's as many solutions to whatever degree polynomial is. So there's two solutions over the complex numbers for a secondary polynomial, or it could be depending if they're complex or real or not. But anyway, so that's presumably why they're giving us both roots, but we only need the one. So it's going to ask us for the a. We get 2 seconds to solve it because, again, well-named function. B, C, and then what it does is it multiplies all that out, and it's going to check whether or not it's 0. And the reason for this here is because of the way when you convert a float, right, because it gives us a float. So so this here is going to be, when it multiplies all this out, it's going to be some number with a whole bunch of stuff after the decimal. In Python, when you convert a float to an int, it doesn't round, it just truncates, drops everything off after the decimal. So if you had 0.999999 and you turned it to an int, you're going to get 0. So this is kind of controlling how close to 0 we have to be, because we need 0 point at least 13 zeros and then some numbers, so that when we multiply it by this, all those are going to get shifted to the left, and we still need that first term to be a 0 to check whether it goes to 0. So now what this is doing is check. So this is a failure check. So right, if we don't, so if it's not 0, we saw here it's going to dump us out. Oh, actually, it didn't dump us out because we didn't even make a guess. But if when it does this, it doesn't equal 0, we're going to fail. Obviously, there's the solution where if we made A, B, and C all zeros, when we multiply that out, we get 0. So it's checking to make sure that none of the AI, BI, and CI are equal to 0. And also, they all have to be between -60 and +60. So we have 2 seconds to guess an A between -60 and +60. Same for a B and a C. And it has to be the solution when it multiplies it all out. This has to be really close to 0. And if we do that, it's going to do it 7 times. If we pass that 7 times, then we move on to the second part, where this is where we get into the elliptic curves. So this is that pi cryptodome function. It's going to generate a random 40-bit prime. And then it's going to use the BI and CI from our last time through the loop as the coefficients of an elliptic curve. If you're not familiar with elliptic curves, like, I don't know, stop watching this video, go find one of the bazillion videos on elliptic curves, because they're actually really cool. But essentially, it's defined over this equation, and if it's defined over a field, then you get this structure. So all of cryptography is built around trapdoor functions. Basically, the computational difficulty in inverting a function. So the example that's pretty much always given is factoring, right? If I give you 2 big numbers, you could sit there and multiply them together. But if I gave you a really big number and asked you to tell me the factors, it's going to be a lot harder. So an elliptic curve is a construction that kind of has one of these trapdoor functions in it. And so we can use it for cryptography, where what they're doing is they're going to pick a random point on that curve. They're going to multiply the point by whatever the value of the flag is, and then get this second point. Now, again, I'm not going to go into how that works, but essentially you can just think of it as an operation, right? There's a way to add points, and if you add this point to itself, however many times the flag is, you get this other point. And the trapdoor function is that it's really easy to do that this way. Right, obviously it's easy. We're doing it in this challenge. The computer can just spit this out. But it's really, really hard to go the other direction. If you give me a point and another point and tell me or ask me how many times did I have to add that first point to itself in order to get the second point, it's really, really hard. It's like factoring a large number. It's a lot harder than going the other way. So this is called so in general, that kind of construction where something multiplied by itself some number of times gives you something else, that's called and you need to find out what that number is called the discrete logarithm problem. And on an elliptic curve, it's called the elliptic curve discrete logarithm problem. But there's a lot of cryptographic primitives built around the discrete logarithm, like Diffie-Hellman, Elgamal. There's all kinds of stuff like that. So it gives us the original point, the ending point, and the prime number that the elliptic curve, the field for the elliptic curve, and then we know BI and CI, right? Because we gave it to them to solve that last iteration. So we have everything to reconstruct this elliptic curve. So then we have to use that to figure out what the flag is. Okay, so let's talk now about how to solve that. And I'm actually going to go ahead and start my solve script because it takes a little while to run. And then there can be fun flashing things to stare at while I ramble on. And hopefully we find the solution before I'm done rambling. So I kind of carved my solution up into 3 parts just to make it easier for the video so it wasn't all cluttered. Obviously, that's not what I would do normally. But so here, for this first part, right, solving the quadratic. if you weren't sure what to do, or kind of like the absolute, like if you think about it, just the simplest way to do it is we know they're all between 60, right? Or negative 60 and 60. So the absolute simplest way to do it would be, let's just check them all and find out if, find which one it is. That'd be like the naive solution, like brute force. Let's do them all. And it might seem like we don't have enough time. We only have 2 seconds, but computers are fast, so that gives us plenty of time. So that's what this solution is. Like literally the most straightforward, easiest way you could do it. So we're going to check all the possible A's, all the possible B's, all the possible C's. I literally just copy and pasted what they're doing right here, and then changed their if statement, right? Because they were checking to see if you failed, and we want to check if it succeeds. So now it's if the result is 0 after we turn it into an int, and none of the i's are 0 for AI, BI, and CI, right? And we don't have to check whether or not the absolute value is less than 60 because we controlled that going in. So this would be kind of like, there's faster ways you could do this. And I guess, like thinking about it, at first I was kind of disappointed. I was like, oh, I wish they'd have made it like, they could have made the range we had to check it farther so you couldn't brute force it in 2 seconds, or made it closer to 0 or something like that. But then really you're just getting into like, people aren't coming to HackTheBox to do leak code or, Project Euler or anything like that. But I still think it's cool because, cryptography it's the intersection of math and computer science. So like you do need to know, algorithms and complexity and that kind of stuff. So I still think it's cool that, and if you're not a programmer, like you probably haven't done a bunch of leak code or Project Euler or anything like that. So this might have been new for you. And even just thinking about how to brute force it all could potentially have been like, valuable learning. Now there, like I said, there's faster ways to do it. Like we could do it I didn't really spend too much time thinking about it, but like they're giving us this x. So really what we have is a linear equation, right? We have, a times some number plus b times some number plus c equals 0. So we could do it in 2 loops instead of 3. There's symmetricalness of answers. There's probably some like really smart linear algebra ways. We're essentially just looking for the solution really close to 0. So I don't know, but we only have to do it the simplest way in order to solve it. So that's all this does. Just does it the simplest way possible. And so in my solution, and the other thing is, if you're kind of new to this stuff, maybe not have used Pwn tools, and you don't have to use Pwn tools. We're just connecting to, server. Like there's tons of different things you can do to do that, but kind of the way I always do it, and the way I learned it, and I see most people do, is you just use Pwn tools. Pwn tools was made for this kind of thing, for CTFs and stuff. So, and I sort of separated everything in the Pwn tools out into its own little class, just again for this video, so everything wasn't cluttered in one file. But essentially, in Pwn tools, like you connect, and then these are so like here is like I'm getting the what it's outputting. So we want to know the x. So like it gives us this string. So in one Pwn tools command, I'm receiving this string, and then I want to extract what the x is. So I'm using this regular expression here. So essentially it's just going to search the string for where x equals, and then it's going to capture if there's a minus sign, any number between 0 and 9, or a point 1 or more times, and then it's going to return that. So that's how I get the x. The same when I'm like sending the quadratic coefficients, right? I'm just sending after I receive the a, then I'm sending the stuff that I tell it to. So again, this isn't like a video. I mean, I'm not going to go into how to use Pwn tools, but like this was a good challenge if this was your first time to like use something like that. Like it's a good tool to know and to use. And like I've got all these. I kind of like Pwn tools because you can do all these like kind of fancier debug statements, which is kind of what's going on here, right? Like I'm setting it up so it's changing it. So instead of just everything raining down the screen, it's kind of like kept on its own little thing, which I like. But so my solution, what we do is let me go over the elliptic curve stuff. So that's essentially how you would solve the quadratic, right? We're just going to brute force the whole space, find what the A, B, and C, find an A, B, and C that works, and then we're going to send that off to them. So that's going to work, and then we're going to get to this elliptic curve. So let me explain then how you solve this. Now, when I talked earlier about factoring, yes, it's a trapdoor function. It's harder one way than it is the other, but unless I give you a really, really big number, you can still do it, even if it does take it harder, right? Like, if I asked you what the factors of 143 are, you could figure it out. If I asked you what the factors of, some like 200-digit number are, you're not going to be able to. So elliptic curve is the same way, but the number in this case is how big the field is essentially. And if you kind of do some crypto challenges, or you can even just learn how many bits you need to have in order to have it secure, 40 isn't enough. Like we can solve this problem for a field that is 40 bits long. So you think, oh sweet, then all we have to do is just solve that. Well, is kind of where the problem comes in. So it's sort of like, let me explain it using just like kind of regular sort of modular arithmetic over the integer. So say we're working mod 11 and I asked you, so same kind of discrete, logarithm, like how many times, what do I, or would be discrete logarithm, but like, what do I have to multiply? So if I had 2 was say my point, and I multiplied it by some value of the flag, and then it came back, and you're not going to get the value of the flag. You're going to get the value of something modulo 11. That's what the flag is going to be equal to, modulo 11. So I can multiply 2 times the actual flag, but you're going to get 9. Well, that doesn't tell you the flag. It just tells you that the flag is congruent to 9 modulo 11. Hopefully that kind of makes sense. So we can solve this, but there's not enough. We're going to get some answer modulo whatever the order of this point G is, right? Because there's only so many times you can multiply G by itself before you get back around to G. So the order of an elliptic curve, there's a Haas's theorem. It's something like, it's essentially, the value of whatever the field is, roughly plus or minus 2 times the square root of that. So it's going to be around 40 bits, and 40 bits is only 5 bytes. So unless our flag is 5 characters long, we're not going to have enough information. So we need a way to combine all that to like get it. So what we can do in the same way with the modular arithmetic I just talked about, if we worked out, if I told you the flag was congruent to 9 modulo 11, and then I said the flag was congruent to, 42 modulo, 101, like you can get a whole bunch of these congruences and then use something called the Chinese remainder theorem to combine them all together. So if you know what, X is congruent to this number, mod something, X is congruent to some other number, mod some other number. You can essentially kind of like build it up until you can get it modulo some number that is bigger than the flag, and then we'll know what it is, what the flag is. Hopefully that makes sense. And it's actually really easy for us to solve. Like, there's a lot of interesting math behind like how you would solve the discrete elliptic curve discrete logarithm problem. Well, we don't got to know any of that. All we need to do is use Sage math, which again, there's other tools you could use or other things you do, but kind of like everyone uses Sage. And so my solution here, normally I would write it in Sage, but I just moved computers and I was having problems getting Pwn tools to work with Sage. So I just did it in Python and imported Sage into it anyway. Kind of getting Sage set up as its own little fun task, which is something I encourage you to do. Here I'm just using the Docker. Anyway, so all we have to do is just reconstruct the elliptic curve with the stuff they told us. So, we're using that B and C, and then I guess technically, so since P is a prime, you can use Z mod, but none of this probably makes sense. But you could also, really the way you do it is use a Galois field. But in this case, it works the same. Anyway, that's kind of what this would be a good problem if you hadn't used Sage math before, is trying to like figure out, learning how to construct an elliptic curve. Just kind of a couple simple things. But essentially, we rebuild the elliptic curve because we know the field and we know the 2 points or the 2 coefficients. We tell it, hey, G is this point on the elliptic curve, right? We're just passing in the value. I should have printed it out so we could have seen what one looked like. But it's just an X and a Y coordinate. And then we're giving it the other point. And then we need to know what the order is. And there's lots of interesting algorithms to do that. But again, we don't need to know any of these. We're just going to have Sage math do it for us. We just say, hey, what's the order of that point on this elliptic curve? And then we're going to solve the discrete log. We're going to say, hey, here's this point I ended up with. Here's the point I started out with. Here's the order. The operation is addition because, like I said, we're adding points on the elliptic curve. Where typically discrete log, you're multiplying, but here we're adding. And we're going to say, hey, solve the discrete log. And it's going to solve it. And it's going to say, okay, over the order of this curve, you had to multiply that point n number of times to get this other point. And in the same way I talked about earlier, like if something is congruent to 9 mod 11 and it's congruent to 3 mod 13, like it's going to be congruent to 42 mod 143. So like we can keep building that up. So we have an instance of it. We know, okay, the flag, we only don't have enough because we only had 40 bits information roughly, but we know, okay, it's going to be congruent to this number over this modulo this. So let's just keep solving it. So that's what, so each time through, like this would solve it once. And then, so that's what we're doing. We're starting out with the flag, which just started out, we don't know anything about it. So I'm going to run a while loop because I don't know how many loops it's going to take, but I'm going to run a while loop. And while the flag, I know the flag starts with HTB, curly braced. So while the flag doesn't start with that, I know I haven't figured out what the flag is. So just keep doing this loop. And then these are just debug statements so I can make it all pretty. And then I wanted to know how many loops it takes or what number loop we're on. So I'm counting the loops. Here again, this is where, like I said, I divided out all the Pwn tools stuff into its own class so it didn't clutter everything up. We're going to open the connection, just some more debug statements. And here's that 7 times through that loop where we're solving the quadratic coefficients, right? I'm getting what the X is that they give me. I'm computing what the A, B, and C are with our brute force solution. And then I'm sending it back to it, inputting the answers. And then I'm going to get, it gives us that elliptic curve. So then I get the information we need to reconstruct the elliptic curve, some more debugs, and then I solve it. And then we need to save these, right? So I'm saving the n in its own little thing and the size of the order in its own other little list. And then what I'm doing is, so I think I mentioned that the Chinese remainder theorem is how you kind of combine all those up. So we're going to do the Chinese remainder theorem on those, that's just what this solution is. Again, I just stuck it in here because it needed, this is a CRT is a Sage function, and I wanted to keep it all in one separated thing. And it's going to update what the flag is. So like, great, now we know the flag is congruent to 42 modulo 143, but that's still not enough, right? The flag is huge, so we're going to have to keep building it up. So then we hit back to the top of the loop again, and it's like, does the flag start with that? Nope. So then we keep running it, and then finally when I solve it, we get the flag, which is, we see it did solve. The flag was 630 bits long, and I'm being a jerk and not giving you the whole flag. So if you want to actually input it and get credit for it, you're either just copy my code, but I really would urge you to, like, if you watch this video and you kind of think like, oh, like if you didn't get the challenge or you kind of were struggling with it, like depending on what part you were struggling with, right? Was it elliptic curves that you weren't familiar with? Was it just how do you connect to the server that you're struggling with? Was it using Sage Math? Like, hopefully this video helped make it sense. I would encourage you to be like, hey, wait a day or two, so this like not super fresh, so you're not basically just like copy pasting everything I did, but then like, but you still have an idea of like, okay, here's what I need to do, and then like go do it. That doing it yourself, even if it's now that you know how to do it, is going to be infinitely more helpful than if you just like, oh, okay, that makes sense, and then you put in the flag and think you'll remember it. And so anyway, I'm basically being a jerk and trying to force you to like get some practice. So let me just run it again so you can so see what we're solving, going through on the loop. Right now the flag isn't anything, and then you can see, if you were watching any of that while I was busy rambling, sometimes it takes a little while. Like right now you'll see it, sometimes it'll get stuck on solving the elliptic curve DLP, because sometimes it's easy to do, right? We're doing it in this amount of time, but it still can take a little bit of time. And see where the flag is gradually growing up as we're combining. The more information we get, we'll know more and more what the flag is modulo some bigger and bigger number, until finally we have a number big enough that we can get the whole flag back. So I don't know, hopefully that made sense. And yeah, I guess that's all I have to say. If you have any questions about anything, please leave a comment. I'm always happy to reply to stuff. If you got anything at all out of this video, if you're still listening to me ramble, like, it'd be super helpful if you liked or subscribed. That really means a lot to me. It's really helpful. Keeps me motivated to like keep doing more stuff. I have a bunch of stuff planned, but if you've been following my channel for a while, I'm not the best at follow through. So help me keep my motivation high. And I hope you got something out of this, and take care.